This is problem number 51 from chapter 26 in Halliday, Resnick, and Walker. It reads that wire C and wire D are made from different materials and have the same length of 1 meter. The resistivity and diameter of wire C are known. They're given to us in the problem, and those of D are also known and given to us in the problem. The wires are joined as shown, and a current of 2 amps is set up. What is the potential difference between points 1 and 2? So this is point 1 here, and this is point 2, the kind of thicker length C of the wire. And also the question asks about the potential difference between points 2 and points 3, the length across the the skinnier wire. What is the rate at which energy is dissipated between those points as well? Let's start with the first question, which is what is the electric potential difference between those points? First, we want to find the resistance across that wire segment C. It's going to be equal to the density, not the density, the resistivity of segment C times the length of segment C over the area of segment C, which can be written, of course, as pi r squared. So that would be length times, resistivity times length over pi rc squared. So all these values are known, so let's go ahead and plug those in. The resistance of segment C is the resistivity, which was given to us as 2 times 10 to the -4th ohm meters, not ohms per meter, but ohm meters. And then we're going to multiply it by the length of 1 meter, and then we need to divide it by pi, and then we need to convert the diameter to the radius and do pi r squared. So the diameter is 1 millimeter. We need to convert it to meters. It's going to be 0.0050 meters. And then we have to remember to square that. When we run that through a calculator, we end up getting 2.55 ohms as being the resistance of segment C. We're going to do the same thing for segment B, except replacing these numbers. So that would be RB is going to be equal to 1 times 10 to the -4th ohm meters. We're going to multiply that by 1 meter, and we're going to divide that by pi r squared, where r is going to be a quarter of a millimeter, or 0.00025 meters. We have to remember to square it. When we do that, we end up getting a resistance across segment D, that should be a D, not B, of 5.09 meters. So now we know the resistance across those segments, and so now we can find the potential difference by just using Ohm's law, V equals IR. So the answer to part A is going to be equal, V is equal to IR, where I is 2 amps, and the resistance is 2.55 ohms plus 5.09 ohms across both of those. That's a total resistance. We get about 10 volts. For the potential difference here. So this is the potential difference across segment D. And then, so that should be part B. Part A, it's going to be the velocity across, the potential across part C is going to be the current flowing through it, which is given to us as the 2 amps, times the resistance across part C, 2.55 ohms, and we end up getting 5.1 volts there. And the last part is asking in part C about power dissipated between points 1 and 2. So I can say simply that I squared R, that's the most convenient method. I already know the resistance, and the current is uniform, it's 2 amps. So when I plug in a current of 2 amps and my resistance across segment C, which I calculated at 2.55 ohms, I end up getting 10 watts for part C. And in part D, I'm going to do the same thing. The power between across segment D, or between points 2 and 3. I can also use I squared R, just using different values. And for part D, I get 20 watts.